Okay, so welcome to today's live interactive session. So today we will be mostly dealing with consolidation. So we will be starting the basics of consolidation, and then we will be solving some problems on the consolidation test, and then we will be solving some problems on the settlement calculation. Okay, so in this week we will be just solving this, and the next week in the seventh week. So in the seventh week lecture, actually, uh, the 1D consolidation equation and all that Terzaghi's 1D one-dimensional consolidation equation, all those things will be discussed. So we will be dealing with them in the next week to determine the time rate of consolidation. Okay, so those things we will be doing the next week, and in this week we will be just uh, solving some problems on the consolidation test, and then uh, the settlement calculation. Okay, and so as we all know that consolidation is actually one of the most important topics in soil mechanics, because uh, the consolidation settlement, because we need to consider the consolidation settlement before like planning our structure over it, construction of any structure over it, over the soil, because uh, as the construction progresses and along the lifetime of the service life of the structure, there is some settlement of the soil. So what we want is that the soil settlement, the maximum settlement of our soil should be happening during the construction, or if we try to using various techniques, what we try to do is that we try to accelerate the process of consolidation of the soil. So consolidation is actually a very time-taking phenomenon. So it takes many years for the soil to obtain 90% plus consolidation. So actually there are many ways to using which we can accelerate the process of consolidation. So those things also we will be studying during the end of this chapter. So to name a few, some techniques are preloading and the use of vertical drains, so which are like, but yeah, vertical drains are actually used extensively nowadays uh, 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 in the practical scenario. So those things also we will be seeing towards that. So now let us start. So before we move into the consolidation, there was a little topic which was discussed, small topic which was discussed at the start, during the start of the sixth week. So that was capillary rising. So capillary rise is actually very clear to you, I guess. So it's nothing that if you put a tube, if I put this hollow tube inside the water, so water will actually rise in this tube. So this is mostly due to the surface tension. Okay, so due to the surface tension of water, this will actually rise. So if we equate the surface tension forces and the weight of the liquid, okay, at the interface, we can actually find the height. We can find the height up to which this water will rise. Okay. So which is this given by this equation. So 4T cos alpha divided by d gamma w, where T is our surface tension forces, right? So these are the surface tension forces. Okay. So for pure water and clean glass, actually this alpha angle with the surface tension force makes with the tube, with the surface of the tube is actually 0. So we get our height of the liquid for pure water and clean glass as this 40 by d gamma. Okay. So Hazen actually in 1930 gave a formula to relate the D10 size. It is a effective size to the height of the capillary rise. Okay. So if my return size is small, if the size of the tube is small, that means you can imagine like this: if the size of the tube is small, then the water will rise to a higher length, right? So if the effective size is less, the age height of capillary rise will be higher. Okay, the C is actually constant. Okay, and if the return size is actually high, then the height of the capillary rise will be low, slower. The height will be lesser. Okay, so this height is actually, so say we have the water table here. So this height is actually this height of the water table. Okay, the height of the water table till which the water is actually going to rise and is actually going to saturate the soil. So we know that the total stress is given by the effective stress for the plus the pore water pressure. So when there is a capillary rise of water, okay, when there is a capillary rise, the effective stress, okay, the pore water pressure at this level, okay, at this level, age height at a height age above the free water surface is actually given by this, okay, minus h gamma w. Okay, so this is actually negative because there is a tensile force, not compressive. It is a tensile force. So there is a suction pressure which uh, acts on the the soil grains, due to which the effective stress actually increases. Due to the suction, okay, so there are soil particles, so there is suction force. So due to this suction force, what will happen? The soil grains will actually come close to each other, and due to which what happens, our effective stress actually will increase. So this is actually this. So what happens? This will actually increase by this amount, h gamma w times. Now, what if our soil is partially saturated? So partially saturated soil. So this is the equation for the pore water pressure given, where we have this saturation for S is the degree of saturation. Okay. So this degree of saturation actually comes into P. Okay. So this was all about this capillary rise. So then we enter into our next main topic, which is consolidation. So consolidation, what happens is that there is a soil, and of the soil we apply some load. Okay. So instantaneously, as soon as we apply some load, what happens is that there is increase in stress in the soil layer. So due to this increase in stress, what happens? Initially there is some elastic settlement. Okay, immediately there is some elastic settlement. Elastic settlement means there the elastic deformation of the soil particles. The elastic deformation of the soil particles, there is an immediate settlement. Okay, so this elastic settlement actually occurs immediately. Now what happens after the elastic settlement? What is there? The soil is completely saturated. Okay, so remember that this consolidation phenomenon is only valid for my this all defined only on the saturated condition. Okay, the definition of the consolidation is valid for a saturated soil. Okay. The soil should be completely saturated. So what happens after the immediate settlement? As soon as my load is applied, what happens? As the soil is saturated, my there is an increase in pore water pressure. Okay, so the increase in the stress is actually completely taken by the pore water pressure as the soil is completely saturated. So this can be explained using a spring model. So we will discuss that spring model in the next slide. So what happens is that as soon as we apply the load, that load is actually carried by the soil or pore water pressure and not the soil particles. Okay, so gradually as we allow the that means gradually what happens as time passes, the water will try to dissipate, try to come out from there. Okay, come out from the pores of the soil. So what happens gradually as the water comes out. So as we allow gradual drainage we allow. So what happens is that the pore water pressure reduces and the effective stress actually increases. Okay, so the load is actually then gradually transferred from the pore water to the soil structure. Okay, the soil grains. Okay, so this drainage of water from the pores actually takes a lot of time because As we know, for clay, the we studied that the hydraulic conductivity is very less. As the hydraulic conductivity is very less, the water actually takes a long amount of time, a large amount of time pass, okay, to travel through the pores. So this process, so this complete process where we apply some load, okay, then there is an increase in pore water pressure, and then there is a gradual dissipation of the pore water pressure due to the drainage of the pore water. And this drainage of the pore water is actually accompanied by a change in volume of the soil. So you can imagine it. It is very intuitive that as water is going out of the soil, there will be some settlement of the soil. So this settlement is actually known as consolidation settlement. Okay, and this consolidation settlement, that is settlement means what? Change in volume. So this volume change actually, there is a gradual volume changes which occurs. So this is known as consolidation, right? So due to this consolidation process is actually very time dependent, and it is actually directly dependent on the hydraulic conductivity of the soil, right? So we will be seeing all these things in next week. So you already might have studied, already might have seen this in the seventh week lecture, where we derived the Terzagh's one-dimensional consolidation equation, where the coefficient of consolidation is related to my Kv value, which is nothing but the vertical value of the hydraulic conductivity in the vertical direction. So, this is the last thing. It is in the last line. You can see it's written again there. The consolidation actually continues for a long time after the immediate settlement. So, immediate settlement happens as soon as we apply some load. Why does immediate settlement happen? Immediate settlement happens due to the elastic deformation of the soil grains, and after the immediate settlement, there is the consolidation. Okay. So here you can see the spring cylinder model. Okay, so in this spring cylinder model, so the soil grains are actually represented using this spring, and you can see that this is actually the water. Okay, the pore water pressure, so the pore water. So the spring and the water. Okay, this is the spring and this is the water. So initially the valve is closed here. Okay, so we are not deriving any drainage. Okay, the valve is closed. So as soon as my P load is applied, so the stress is given by P by A. So my P by A is actually the stress. This is the area of cross section A. So P by A will be the stress. So as soon as my uh, load is applied, what happens is the complete load is transferred to the pore water pressure. Okay, remember the valve is closed now. The complete load initially, what happens, my pore water pressure is zero. As soon as I apply some load, that whole stress is actually this whole stress is shown as is taken by the pore water pressure. Okay, so my U is equal to that applied stress. Okay, the pressure actually increases by that. Now as we open the valve, the water starts to come out. Okay, the water starts to come out. In this state, what happens? My pore water pressure increases. Increase in pore water pressure is less than P by A, obviously, because as water is coming out, the dissipation of pore water pressure is taking place. So due to that, my pore water pressure is obviously less than P by A, and my effective stress, that is the stress actually taken by the spring, or the stress that is taken by the soil grains, is actually not zero. In that case, it will be some amount greater than zero. So what happens after the drainage continues? A stage will come when the extra pore water pressure which was generated due to this load is become zero. Okay, due to the drainage of the water. So due to this, what happens? My pore water pressure, my increase in pore water pressure becomes zero, and this total stress. Okay, this is actually taken by my soil grains. That is, this is shown as this turns out is the effective stress. Okay, at the end of the consolidation, my effective stress is actually equal to the applied stress, right? Because now none of the for this none of the for load is actually taken by the water. Okay, everything is taken by the spring, right? So this is the spring cylinder model. which actually simplifies our consolidation explanation of the consolidation procedure phenomenon. Okay. So here we can see that here a clay, there is a clay layer. Okay, this is a clay layer which is sandwiched between two sand layers. Okay, it means water will be, see, as sand, there is sand in both up, there is sand at the top, there is sand at the bottom. So what happens is that that means we are allowing drainage in both the direction. Okay, we are allowing drainage both at the top and at by the bottom. Okay, we are allowing drainage both in both the directions. Okay, and the height of this clay layer is h. Now the groundwater table is actually positioned here, so my clay layer is actually completely submerged. Okay, that is completely saturated. So this is actually semi-infinite soil which is shown here. That semi-infinite because in the up in this in the z direction, in the depth direction, the height is actually limited. In the other directions, in this direction, and in this direction, it's infinite. So a semi-infinite soil mass, soil mass is shown here. Okay. So what when let us see some of the diagrams which are shown here. So let us see what are actually meant by this. So when my time is at 0, okay, initial time. So you apply a stress here, okay, delta sigma is actually the increase in stress due to some agent, okay. There is some increase in stress, say delta sigma. Due to this delta sigma, at time t equal to 0 means as soon as we apply the delta sigma, let us see the scenario. So what happens? My total stress is equal to delta sigma along this depth. Okay, along this depth, my total stress is delta sigma. And what happens is that as we studied in the previous slide, as soon as we apply the load, instantaneously, what happens? This stress is actually taken by the pore water. Okay, so my increase in pore water pressure is actually equal to this delta sigma. Okay, and my effective stress is 0 because my spring is actually not taking, if you think in terms of the spring cylinder model, my spring is actually not taking any stress. That is why soil grains aren't taking any extra stress, incremental stress. Now what happens is any time between 0 and infinity, my total stress was this. Okay, at any time, at a time greater than 0, what happens is that the pore water starts to dissipate from this direction. So at these drainage ends, these are the drainage ends. So here is drain. So at the extreme ends of this clay layer, the extreme top and the bottom of the clay layer, at the interfaces, my pore water pressure is going to be 0 because immediately the water there is going out. The pore water pressure is immediately going dissipated because there is drainage layer above it. So it becomes 0. Right. So as we come to the middle, you can see that there is a large quantity of pore water pressure, and at the top and the bottom, the pore water pressure actually is 0. And if you see the effective stress is actually equal to the delta sigma value at here and here. Okay, because my pore water pressure becomes 0, and at any depth, middle depth, center, if you see the pore water pressure is not equal to sigma z, but some value which is like uh, greater than 0. Okay, there is some value greater than 0, not equal to c. This is not equal to this, but some value greater than 0. Okay, there is some value. So now we allow more consolidation to take place. So at time t is equal to infinity, the infinite time, what will happen is that along the complete depth, my pore water pressure would have dissipated completely. So my pore water pressure actually becomes 0 here. Okay, completely 0. And at infinite time, my effective stress is total effective stress. That means the total stress, which there was the increase in stress, is actually now transferred as the effective stress, because now none of this increase in stress is taken by the pore water. The complete increase in stress is taken by the soil grains. Okay, so my effective stress is actually equal to this, effective stress is equal to this increasing stress. My water pressure is 0. So this is the situation at time t is equal to infinite. Okay. Now we come to the one-dimensional consolidation test. So in the consolidation test, you can see that there is soil specimen. Okay, the soil specimen is kept in the specimen ring. There is a specimen ring inside which we need to put the soil specimen. Okay, and in the top and bottom there are porous stones. Okay, so due to the presence of the porous stone, you can relate it with the relate it with the sorry. Yeah, so you can relate it to the sand layers. Okay, you relate this as the sand layer. So due to the presence of porous stone, what happens is that we will be allowing drainage in the top and bottom direction. Yeah. So we are allowing drainage here and here. Okay, we are allowing drainage in the top and bottom part. We are allowing double drainage. Also, we can see that this soil is actually completely submerged, completely saturated. Okay, completely saturated. So load is applied here, and there is a dial gauge. So dial gauge is actually used to measure the volume change. So volume change, because see, this sample is restricted in all the directions, right? So the volume change will actually translate in terms of the change in height, right? Change in the height of the thickness of the sample. Okay, so that is actually measured using this dial gauge. So these are some parameters of the one-dimensional consolidation test. You can see the specimen size is generally 64 mm diameter and 25 mm thickness. Okay, the load is applied to the specimen submerged under water. You already seen that. And each load, so each increment of load, so initially applies, you say apply 1 kg load. So initially, what will you just apply the load and you will be taking readings. Okay, so at interval. So you apply 1 kg load. As soon as you apply, you start taking reading in the paper. So for 0 second, so for 1 second this much, for 30 seconds this much, for 60 seconds this much, for 120 seconds this much. So like this, actually we take on the reading. Okay. Then we take for 1 hour. Then after 1 hour, 2 hours. What after 2 hours we take for 4 hours. So like this, we keep on taking the reading of the dial gauge. Okay, for 24 hours. So each load is kept for 24. So after 24 hours, what is done is that my load is actually doubled. Okay, initially if I put 1 kg, then I will next load will be 2 kg. So like this, my consolidation test is actually carried out. So after doing this test, actually what we can do is that we can plot the void ratio versus my pressure, the effective stress or the pressure graph. Okay, I can plot my void ratio versus effective stress plot. Okay, or the log of effective stress, both we can plot. After this, we will see how to find out the void ratio. We will solve two problems regarding that. Okay. So if you see this, so here we have the deformation, okay, versus the time. Okay, this graph actually we will be obtaining for each load. Okay, for each load actually we will be obtaining this graph. Okay, so there will be some deformation, there will be some time. So time is very low. So initially, if you plot the graph, you will see that this stage, first stage, is the initial compression, because due to the readjustment of the soil particles, soil grains, there is some initial compression. And then after the initial compression, there is a part which is known as the primary consolidation, which takes place due to the dissipation of the pore water pressure, the expulsion of the pore water. Okay, that is my primary consolidation. And after the primary consolidation, there is some other part which there is some plastic rearrangement of the grains that is actually known as my secondary consolidation. Okay, so the initial consolidation compression is actually called the preloading. Then I have my primary consolidation, and then my plastic readjustment, which causes the secondary consolidation. Now, after this, what we can do is we can actually plot the void ratio versus the pressure plots. So at the end of each loading, we will get some void ratio. We can calculate the void ratio, and using that void ratio, we will be actually plotting my void ratio versus pressure plots. Okay, and the void ratio is actually determined from the change in height of the sample, right? So how to determine that height? How to determine the void ratio? We will be seeing here. Okay. So the height of solid, okay, the height of solid is actually you can write. So volume of solid, from volume of solid, this thing has come. So volume of solid is nothing but the height of solid divided by the GS into gamma W. Okay, so from this actually we can determine the height of solid. So initially, before starting the soil, we can before starting that test, we know that, or after the test, whatever, you can also do it after this. So you actually know how much amount of weight of solids you are putting in the as a specimen, right? So if you know the mass of the solids, so we can find out the height of the solids, right? Now next part is to calculate the initial height of the voids. Okay, so what will be my height of the voids? Height of the void is nothing but a total height minus the height of, means what is the height volume? Okay, this is nothing, volume of void is total volume minus volume of solids. So similarly, if you write in terms of the heights, it will be nothing but the height of the what will be the initial height of voids. The height of voids will be nothing but the total height minus the height of the solids. So we'll get the height of the voids, right? Then you need to calculate the initial void ratio. The initial void ratio is nothing but the volume of voids by volume of solids. So if you do the height of voids by height of solids, you will get the initial void ratio before the start of the test. Right? You'll get the initial void ratio of the specimen. Now, for each loading increment, say my height actually changes by del h1 times. Right? So initially, say my thickness of the soil was 25 mm. After the first loading, it changes to 24 mm. So this del h1 is actually 1 mm. Okay, so due to this this change in height, we can determine how much change there will be change in void ratio. So change in void ratio will be given by del h1 by hs. So what will be my void ratio at the end of the first loading increment? Nothing but the initial void ratio minus del e1. Okay, so on after the next loading, how to find? It will be E1 minus del H2 by HS. So on, we can find out till the last loading. Okay. In this way, we'll find out the void ratio. So there is another method. Okay. So using which you can actually determine this void ratio. Actually, this is by doing backwards. Okay. We will be seeing how to do this. We will be solving the problems using this method. So it is assumed that my specimen is actually completely saturated at the end of the test. So end of the test. Okay, we are assuming that my sample is completely saturated at the end of the test. Now we know this relation AC is equal to W into G. Okay, so if what will be E final means at the end of the test, E will be given by this, as we are putting S equal to 1, right? And so my void ratio at the end of the test will be given by the water content at the end of the test into G. And how to find the water content at the end of the test? We see the test is over. You take out the sample, you measure the water content using your oven. You can measure it. So you can obtain the water content at the end of the test, right? So using this, we can actually find out my void ratio at the end of the test. Now del H by H is, you can write it as del E by 1 plus E naught. The change in volume by initial volume can be written by this. Okay, from here we can write this. Now what is the void ratio at the end of each effective stress? We just saw in the previous slide also. Okay, so initial void ratio minus the change in void ratio will give my void ratio at the end of each effective stress increment, right? Now where this How to find this change in word ratio? My training word ratio will be given by this, which is nothing but delta H by HF into 1 plus EF from this relation. Just from E naught, we are replacing E naught by EF. Okay. So we will get this. So we will see. This will be clear as we solve the problem. Okay. We will be solving the problems using this relation. Okay. So the next topic is my next thing which is important to us is to understand what are normally consolidated soils and what are my over consolidated soils, or the other names of over consolidated soils are pre-consolidated or pre-compressed soils. Okay, so normally consolidated soil means that whatever load, whatever stress is acting on the soil at this point of time, that is actually the maximum stress it has ever encountered in its life. Okay, so that is actually the maximum stress that that soil structure has actually encountered in its life. And what is my over consolidated or pre-consolidated or pre-compressed soil? That soil means that, so initially say there was a soil which was under 100 kPa stress. Okay, then what happens? Then say you remove 75 kPa stress. So now the soil is under 25 kPa stress, right? So initially, before in its history, life history, before it was in 100 kPa stress, and now it is under 25 kPa stress. Okay, so the stress has actually been released now. So that is actually my over consolidated. So to understand this better, a term is defined which is known as over consolidation ratio, which is given by the maximum applied stress in the past divided by the present applied effective stress. So for over consolidated soil, maximum, say in our example, our maximum applied stress in the past was how much? 75, 100, and our present effective stress is how much? 25. So our over consolidation is actually greater than 1. So we can, for over consolidated soil, our OCR is actually greater than. And for normally consolidated soil, it is actually generally equal to 1. So before also it was 100 kPa, now also it was 100 kPa. 100 kPa is the maximum that it has encountered in this life. Right? So that will actually be my normally consolidated stress. Or why less than 1? Say initially, say before the soil was under 50 kPa stress, and now it is under 100 kPa stress. So my OCR will be less than 1. So that's why it is known as, it is also known as under consolidated. Okay, normally consolidated, under consolidated at that time. So it will behave. So in that case, my OCR will be less than equal to 1. So it is a normally consolidated or under consolidated. So now there are some terms, say like coefficient of compressibility, compression index, coefficient of volume change. Okay, so let us actually uh, look into this. So what are actually all these terms? Okay, so yeah. So when we actually plot our E versus by effective stress graphs from the consolidation test, actually when we plot, so for normally consolidated clay, actually, see, this is E. Okay, this is my effective stress. We get this kind of graph. Okay, and if you plot in the log scale, you will get something like this. Okay, on semi-log scale. And for over consolidated soil, this is for NC, this is for C, something like this. Okay, so these are the types of graphs, E versus log of my effective stress, or E versus effective stress plots that we will encounter for normally consolidated clays and over consolidated clays. So by looking at the graph, actually you can guess what kind of soil it is. Okay, now what is coefficient of compressibility? So coefficient of compressibility is nothing but the slope of this graph. Okay, the slope of my E versus effective stress plot. That is my coefficient of compressibility. Why there is a minus sign? Because with increase in effective stress, there is a reduction in the uh, this word ratio. So there is a negative sign. Now, what is my compression index? My compression index is the graph of these plots. That is the E versus log of the effective stress plots. That is my compression index. What is the coefficient of volume change? The coefficient of volume change is given by this. That is the coefficient of compressibility divided by 1 plus initial velocity. Right? Now there are more terms like swelling index and recompression index. So swelling index means the initially you are loading the soil and then you are reducing the load in the soil. So what happens is that there will be a swelling in the soil. So the slope of that graph in the E versus log of effective stress plot is actually known as the swelling index. And what is the recompression index? Say first you are loading, then you are unloading, then again you are loading. Okay, again you are loading. So that will be actually my recompression index. We will discuss. Okay, so this recompression index is actually 1/5 to 1/10 of my CC value. It is 1/5 to 1/10 of my CC value. Okay, so one more thing I want to draw is yeah, I just want to draw the E versus log P graph. Okay, so S clay, which is initially over consolidated and then it is normally consolidated. Initially it is over consolidated and then gradually it is normally consolidated. For that, how will be the graph? Okay, and also you will see the recompression and compression curve, swelling graphs. Okay, so initially it will be like this. So up to this point, okay, up to this point actually my soil will be over consolidated, and after this point my soil will be normally consolidated. Okay, we will get like this curve. Okay, then what happens? Then after that, after coming to this point, we are actually unloading it. If you unload it, it will come here, then again we will reload it. This will be okay. So our graph will actually look like this. Now, say there is soil. Okay, there is also, this is actually known as the pre-consolidation pressure. Okay, pre-consolidation stress. Pre-consolidation stress. Okay, so this part is my over consolidated part. Okay, so initially say my soil was in his history, in his life history, the soil had undergone a stress up to this point. Okay, then there was reloading, there was so then that stress was removed. So the graph which we get from here to here is actually will be like this, will be same to the OC part. And then after this point, the graph which is we are getting is known as the virgin curve. Why virgin curve? Because for the first time the soil is undergoing some consolidation with due to the stress which is greater than this stress. Okay, it is greater than this amount of stress. Okay, that is the maximum amount of stress. Okay, so this was the maximum amount of stress which it had undergone in its life history. So after that, so there are techniques which we can find these things. We will be seeing in the future. So there is some graphical method we can find this stress. Okay, so this is not the virgin curve. So after what happens, after coming to here, we are again reloading this to zero stress. So one interesting thing to note here is that even though we reload this to zero stress, my initial word ratio was this. So here the word ratio doesn't actually come back to E naught. Actually, right? So it is some value always less than E naught. We cannot go back to this value because there is some permanent deformation that is occurred in the soil mass. So then there is again decompression. Okay, decompression, and then we are ending the So this is the normally considered. This is the uh, expansion or the swelling, and this is the decompression. Okay, so we studied the swelling index. So this the slope of this curve actually is the swelling index, and the slope of this one is the actually this line is actually the decompression index. Okay. Now let us actually start solving the problems. Okay, so one or two problems are there, I think, related. Then we will be going into the consolidation. Okay. So so my first problem is that we have to compute the maximum capillary tension of a tube of 0.12 mm in diameter at 4 degrees. So what we can do is that we know that HC is actually given by 0.3084 by d centimeter. Okay, so 0.3084 divided by 0.012. If you do, we will get 25.7 centimeter as by height of capillary rise, which is nothing but 0.257 meter. Now, what is the capillary tension? Capillary tension is nothing but H into gamma W, nothing but 0.257 into 9.81, 2.521 to 5 meter square. Okay. So see, we had learned the Huygens formula, right? D10. So from there only you are getting this. If you put C and E say, so we are getting some constant. So directly here we are putting the constant. So from there we are getting this. Okay, so the next question, the capillary rise in a soil having D10 is equal to 0.07 mm is 49 centimeter. Estimate the capillary rise in another soil having D10 as effective size as 0.12 mm. Assume same void ratios in both the soils. Okay, same void ratios we have to assume. So we can write like this. So what was my formula was H by C D10, right? So I can write H into D10 is equal to constant, right? H by D10 is a constant. So for 49, it's wait, yeah, 49 it's 0.07, right? And we have to find out for 0.12. Okay, so H into 0.12. From here you can get my H, right? So these are the two simple problems, nothing, just based on the Huygens formula you can find out the capillary height of capillary. Yeah, so now let us come to our main topic, which is consolidation. Okay. So these are some observations that were recorded in a consolidation test, right? So you can see there is applied pressure, and below that there is final gauge reading, means the reading of the gauge is there. Okay, the dial gauge in mm, it's given. Okay, so initial height of the specimen is given as 20 mm. Initial height we have 20 mm. The diameter of the specimen is given as 75 millimeters. GS is given, means the specific gravity is given as 2.77, and the final water content is given as 39%, right? So what we need to calculate is that we need to calculate the void ratio corresponding to each pressure increment. Okay, so we need to calculate the void ratio. So we finally, ultimately, what we need to do, we need to actually plot the void ratio versus our void ratio versus this pressure effective stress plots. Okay, so in order to plot my void ratio versus effective stress plots, actually uh, we need to find out the void ratio. So let us see how we can find out the void. So as I had discussed below, so yeah, discussed before, so my final water content is given, right? So if my final water content is given, from the final water content, what can we calculate? We had just discussed a few slides back. My G is given, my final water content is given. So what can we calculate from this? Final water content is given and my G value is given. Okay, so what we can do is we can easily calculate the void ratio at the end of the test. That is my E final, which will be nothing but my final water content into the GS. So what is my final water content? Final water content is 39%. So 0.39 into 2.77, nothing but 1.08. So we get our final void ratio, right? Now, what is the initial height of my specimen? What is the initial height? My initial height is given as 20 millimeters. Okay. And at the end of the test, what is the height of my specimen? See, how can we find that out? So my initial gauge reading was 100 mm, right? And my final gauge reading is my 766 mm. So what is the change in delta H, change in height that is occurring? How to find that out? So my delta H is nothing but 766 minus 100 to, that is 6.66 mm. That is a change. So what will be my final height? At the end of the test, think about 13.4 mm, right? So initial height we had 20 millimeters, and then my final height is actually 20 minus 6.66 millimeters. Okay, which is something like 30.34 millimeters. Okay, and the change, how did we find out? So from here we can see that initially 100 was the gauge reading, finally it was 766 is the gauge reading. So we found out the change in the thickness from the starting to the end of the test, and that we deducted from the initial height, we got the final height, right? So this is my H final. Now we have determined the relation where delta E is actually H by HF by 1 plus EF, right? The change in the void ratio is nothing but delta into the delta is change in height where by the final height into 1 plus EF is the final void ratio. So let us put all the terms. It's nothing but 13.34 1 plus 1.08, nothing but 0.156 delta H, where delta H is in mm. Okay, so we got this, right? Got this relation. So now let us make the table. So we will be solving it in a tabular form, so it will be very easy for us. So fine, the first it will be my pressure. Okay, what are my pressure? 0, 50, 100, then 200, then 400, then 800, then again 0, right? With the pressure. Okay. Then we have the dial gauge reading. Dial gauge reading. So we know it was 100, then 359, 299, 632, 768, 899, 66. We have the dial velocity. Then we have the change in height. Okay, in mm. We will write down. So what are the change in height? So from here to here, how much mm there is change in height? 359 minus 100, 259 into 10 to the power minus 2. It is minus 2.59 change in height. So height is reducing, right? So this much is the changing height. From here to here, how much is the change in height? Okay. From here to here, how much? If you can say from 499 to 632. 1.33. From here to here, how much is changing? Minus 1.36. Then here to here, 1.31. Again from 899 to 766. How much? It is actually increasing. Increasing by how much? Why it is increasing? Because from 800 we are releasing the load, like we are making it to 0. So our final height is actually increasing. From 899 it will be actually increased to 1.33. Right? Now, if we have the changes in height, we can find out the thickness of the specimen. So initially it was how much? 20 mm. Then it is 17.41 mm. Then it is 16.01 mm. Then it is 14.68 mm. Then 14.68 minus 1.36, but 13.32. 13.32 minus 1.31 is 12.01. 12.01 plus 1.33 is 13.34. Okay. So we got this heights. Next, we have my delta I. Delta I. It is my change in void ratio. So what was the relation for change in void ratio that we determined? This change in void ratio is 0.156 into delta H. So this is nothing but 0.156 into delta H. Okay. Okay. So if we do this, we can find out the change in void ratios. Right. So for this one, what was the change in height? 0.259. So 0.259 into what? Sorry, 2.59 into how much? Okay, see, there is a catch here. What we will be doing is that we will be actually, okay, we can do from top also, you can do from bottom also. Okay, next, let us do from top only. Okay, okay, so it is 2.59 into 0.156. Should be nothing but minus 0.404, then 0.156 into 1.40 should be nothing but minus 0.218, then this into this, nothing but 207, then we will have minus 212, minus 0.204. Then at the end, we will have plus 0.207. Okay, so we got the change in the void ratios, right? Change in the void ratios. Now, what we can do is that we know, sorry, this is my E. Okay, so we'll just as we start from the bottom. Okay, So what was my final void ratio? I had found out my final void ratio as 1.08. So I know my final void ratio is 1.08. Right? Now 1.08 plus 0.207 will give me this void ratio. So 1.08 plus 0.207. I have 1.287. Sorry. Extremely sorry. 1.08. Yeah. So we write down, it will be minus, right? There is minus. So 1.08 minus plus this one will give my this term nothing but 0.873. Then 0.873 minus of minus 0.204 is plus 0.204. Give my next 1.077. Okay. Then again 1.077 minus of minus 0.212. Nothing but 1.289. Then again plus 0.207. 6 plus 0.404. Sorry. 1.496 plus 0.218. 1.714. Then plus 0.404. 2.18. So from backwards, we actually go to the top. Okay, we go actually like this. So finally, we got from the final void ratio we started, and we reached up to the initial void ratio. So in this way, we complete the graph, complete the table, and then what we can do is we can make our void ratio versus pressure plots. Okay, so initially pressure was 0, it was here some 2.118 here somewhere. Then when it was 50, it was here. So some graph we will get. So, okay, so I suggest you want just plot and check once how the graph actually comes in both this scale and also in the semi-log scale. Okay. Okay, I hope this is clear how we calculated everything and then we went from bottom to the top. So yeah, so now let us come to our next problem. The next problem is also quite similar. Here what is given, the following observation are recorded in a consolidation test, each load being maintained for 24 hours. Okay, so each load we are maintained for 24 hours. Here is the final order. Now here what values are given to us? The applied pressure is given and the sample thickness is given. Okay, in the previous case our dial gauge reading was given, using which we will determine the change in thickness, and then we determine the, it was not actually required, but still we determined the heights. Okay, height of the soil. But now in this case directly my sample thickness is given. Okay, so how will we actually solve this? So initial yeah, so initial procedure will be actually quite same. Same to the previous one. So if you can tell me what will be my first step. So my final water content is given, right? G value is given. So what can I determine from this? I can find out my final void ratio. G is given. Okay, G is given and E is given. Sorry, W is given. My saturation is 1, because you're considering that at the end of the test my soil will be completely saturated, right? So what I can do is I can determine the final void ratio. So let us do that first. So 0.28 to 2.72. How much is it coming? 0.28 into 2.72. Give me 0.762. Okay. Now we know that del h by h is nothing but we can write del e by 1 plus e naught. Okay, so if h is my initial height and e naught is my initial vertice, I can write this. Correct. So from here I will get, see, you will, so what we will do is that we will take only these two. Okay, we will take these two loading increments. Correct. So we will make use of the last two loading increments. So it will be 18.36. Okay, 18.36 minus 18.90 by my height. It is 18.90. Okay, it is this. Okay, you can write f also here. F also you can write. So nothing but delta E by 1 plus 0.762. Right? So delta F I know. Okay, final height I know. Now I'm making use of this to determine the delta E. So what will be my delta E if I do here? 1.762 multiplied by 18.36 minus 18.90 divided by 18.050 minus 0.050 mm. Okay, so what will be my E? Means what will be my void ratio at this stage? E will be, E1 will be EF minus delta E 0.762 and 0.050, actually 0.71. Okay, so we knew the void ratio here. So from there we find out the void ratio at this stage. Okay, E1. They're calling this at E1. So this one we knew. From here we determined this one. But similarly, what we can do is we can determine for all the this one, all the stresses for each stress stage you can determine. Let us make the table. Okay, tell me the stress. Then I will have my H in mm, delta H, delta E, okay, 0, 50, 100, 200, 400, 800 and 0. These are actually everything is, these are all given values that I'm writing. Okay, so from here to here, how much it changes? Minus 0.4. From here to here. Then from here to here, how much it changes? Minus 0.15. From here to here, how much it changes? Minus 0.30. From here to here, minus 0.29. From here to here, minus 0.20. From here to here, plus 0.45. Okay, so this final void ratio I know already. What was my final void ratio? 0.762. 762. Then I determine this delta E was 0.050. Right. So from here to here, I got this first one, which was 0.712. Right. Again, what I need to do is that I need to determine this value. Okay. It's from here to here, how much is by, or from here also you can. So if you want to deduct from the EF, what we will do is that we will take the changes from here to here. Okay. How to determine this? Let us see. EF. So initially it was yeah. So it was 18.36. From 18.36 it has become 18.56. Okay. From 18.36 it has become 18.56. So 18.36 minus 18.56. Actually it was 18.36. If I put here 0.712, I can put 0.712. If I do this, I will get 18.36 minus 18.56. Minus
0.3424.
How much?
Minus 0.3424.
I am getting minus 0.019.
019.
Yeah. You do this, okay? This one. Are you doing from this to this? I am considering these two now.
Right, same.
Same, na? Please solve this one. It should come minus 0.019.
Right. It's right.
Okay, na? Yeah, so you will get here minus 0.019. Okay, so 0.712 is E. Okay. So 0.712, actually it will be plus point, so minus of minus it will be plus. So 0.712 plus 0.019, it will give me 0.731. It will be 0.731. Okay. Now again, considering these two, we can calculate these two again. If we do 18.85 minus 18.56 divided by 18.56, 1 plus 0.731. If we do, the delta E should come out as minus 0.027. Are you getting this one? Minus 0.027 plus 0.027 is coming, right?
Right.
So 0.731 plus 0.731 plus 0.027, you will get 0.758. Okay, so why this kind of problem is actually important, because we will be doing we generally do some tests, consolidation tests, right? So if we do consolidation test, we have to do this calculation, otherwise we cannot find the word ratio. If we cannot find the word ratio, we won't be able to plot our word ratio versus these plots, word ratio versus pressure plots. So we need to be very clear how to solve, how to find out my e's from the height values. I have to find out the word ratio from the high value. So that's why these are actually very important. These kinds of problems are actually really important. So now let us find again. Let us take 200 and 100. Let us take these two and again find again 10.1, 10.85, 10.89 to 1.758. Go to B 0.028. So 0.028 plus 0.758, I will get 0.76. Okay. So again, considering these two, it's 19.15 minus 19.30 divided by 19.15 into it will be minus 0.014. So plus 0.786 to 0.8. Okay. Now last, please do this one for these two, 0 and 50. These two. Please tell me the delta E.
Minus 0.035.
Minus 0.03.
5.
Okay. So 0.8 plus 0.035. 0.835. Okay. So we completed our table. Again, we started from the bottom and we gradually went to the top. So we got, finally we got the word ratios for each of these stress increments. So we can now plot this or E versus log P graph. Okay. Yeah. So I hope this was clear. Yeah. So now let us come to the fifth problem. So in a consolidation test, the void ratio of the specimen was 1.052 under the effective pressure of 207 kilonewton per meter square. Okay, and this changed to point void ratio actually reduced to 0.932 when the pressure was increased to 430 kPa. Okay, or kilonewton per meter square. So as we increase the pressure, uh, this void ratio reduced. Now we need to calculate the coefficient of compressibility, compression index, coefficient of volume compressibility. That is CC. Now first on AV, CC, and MV. So these three parameters we need to calculate. So let me write down the data. So E1 was F2 and the sigma 1 of sorry, 430. Okay. So this data is actually known to us. So this data is given to us. So can you tell me what was the formula for coefficient of compressibility, AV? What was AV? Coefficient of compressibility. What was the what is coefficient of compressibility? What is the coefficient of compressibility? Yeah. This is some slope, right? So slope of which curve? AV is the slope of which curve? If you can tell, the coefficient of compressibility is the slope of which curve? Which graph? Void ratio versus
Yes, sigma pressure, delta V upon delta E.
so the coefficient of compressibility is actually the slope of my void ratio versus the pressure curve, okay, or the effective stress curve, right? So what will be this? Equal to delta E by delta sigma. So just put the values delta E. What is my delta E? 1.052 minus. So what will be the value? Just calculate 1.052 divided by 2, 30 meter square plus 5 kilometers per. So this was our AV. Now next is my compression index. So can you tell me what is the what is compression index? What is compression index? This is also a slope, right? Slope of which line? Compression index is also a slope. See, my before we studied the coefficient of compressibility. The coefficient of compressibility is the slope of my E versus effective stress curve, right? Now, what is my coefficient of compression? Compression index. Compression index is also a slope of some line, okay, which or slope of some graph, okay. So this is a slope of which plot? Compression index is the slope of which plot?
Void ratio versus a log of
Yeah,
stress.
yeah. This is the slope of the void ratio versus log of the effective stress curve, right? So if you plot void ratio versus log of the effective stress for normally considered soil, it will come like this, some straight line with reducing slope. So the slope of this line is actually my CC, right? So CC is nothing but minus delta E by log 2 by, okay. So if we put the values minus 2 minus 1.05 0.052 right, 430 by 207. Okay, so this is my compression index. So please find out the value. In 377. Okay. So I hope this was clear. So initially, this is the line. So for some, so for E1 207, and when my load is increased to 430, this is my E2. Okay. The slope from here, we actually found out the slope. It is nothing but my CC. So does CC has any unit? The unit of coefficient of compressibility was meter square per kilometer. So what is the unit of coefficient of compression index? Sorry, what is the unit of compression index?
Meter square per.
No. See, it doesn't have any unit, right? So void ratio doesn't have unit. And here also see pressure by pressure or stress by stress, so no unit. So it is that's why it's called a index because it doesn't have any unit. Okay. It will be just a number. So next you need to find out the coefficient of volume compressibility. Is MV. What was the formula or relation for MV? What was the relation?
AV upon 1 plus E naught.
Yeah, AV upon 1 plus E naught. So do you know how this AV upon 1 plus E naught has come? So this coefficient of volume change is actually defined as the ratio of unit volume change per unit change in effective stress. Okay. So this is actually defined like this: minus del V by V by per unit change in effective stress. So we can write this as this. You can write now del H by H. You can write this like this. Now what is del E by sigma? Say this change in sigma stress, nothing but AV. So finally we get AV by 1 plus E. Okay, that's why we are relating this is the change in volume per unit volume with respect to change in effective stress. Okay, that's why it's known as coefficient of volume compressibility. So AVI, I know I have already calculated. What was my AV? It was maybe it was 5.38 into 10 to the power minus 4, 1 plus E naught. E naught here is 1.052. So I will get 2.62 into. So does this MB have any unit? Does coefficient of volume compressibility have a unit? Hmm?
Yes.
Yes. What is the unit?
Meter square
Per kilometer. This is same as the unit of my AV, right? E naught doesn't have any unit, so it will be same as the unit of the AV. Okay. So we calculated all the three requested parameters, which were the coefficient of compressibility, compression index, and the coefficient of volume compressibility. So the next problem is actually not from consolidation, it's actually related to immediate settlement. Okay. So for a flexible foundation with sides 2 meter to 3 meters, so 2 meter by 3 meter foundation is there, and axial load acting on the foundation is 750 kilonewton. We have to determine the elastic settlement under one of the corners. Okay. Soil has a Poisson's ratio and Jones modulus as 0.37 and 9 9.8 megapascals respectively. Use IT. So since the length and width of the footing is given and the axial load is given, so we can find out the stress acting on the at the base of the foundation is nothing but 750 to nothing but 125 kPa. Okay. Oh, so it will not kPa, it will be Pascal. Okay, because we are multiplying by 10 to the power 3, so this is 125 pascals. Oh, 1 second. Let me write in kPa on. Okay, 750 by 3 into 2, so it's 125 kilopascals is my pressure. So there is a footing. Okay, there is a footing like this. Okay, so 2 meter by 3 meter footing is there. At the base of the footing, this much pressure is actually acting. Now we have to find out the settlement below the below one of its corners. Okay, so actually the immediate settlement of the elastic settlement, okay, is given by this relation QB 1 minus mu square ES into IT. So this IT influence factor actually changes where you want to find out the settlement. Right? So settlement, so as the foundation is flexible, the settlement is actually not same. See, if the foundation is rigid, if the foundation is rigid, the set when it settles as a rigid. Okay, settlement is like this. But when the foundation is not flexible, the settlement is actually something like this. Okay, it will settle and it will actually be flexible, so it will bend. So the settlement below each point, below the center and at the edge will be actually different. So this influence factor actually gives that value, how the settlement actually changes. So this IT directly is given here as 0.70. So we will see in the later chapter. I don't know if it will be taught or not. So it's actually comes under our foundation design and all those things, those topics. So here my IT sequence, so just I will put the values. My Q value I know 125. Okay, 125. My B I know. Width, what is the width? With touching but 2 meter, this width is 2. Okay, 2 meter. What is my Poisson ratio? 1 minus 0.37 square. ES is what? 9.8 MPa. So I will write 9.8 into 10 to the power 3, it comes changes to kPa, and IT is 0.70. So if we calculate this, my immediate settlement will actually come out as 15.41 minus 3 meter, which is nothing but 15.41 millimeters. Okay, so this is the immediate settlement that immediately occurs after you load the soil. Okay, not consolidation settlement. Okay, this comes from the elastic theory. Okay, not the consolidation theory. So this is the immediate settlement. Now let us come to this next problem. Standard soil has a compression index of 0.28, means CC is given, right? Compression index is given as 0.28. Its void ratio at a stress of 12 kPa is this much, and permeability is also given. Okay, compute the change in void ratio if the stress is increased to 21.6 kilonewton per meter square, and the settlement in the above case if the soil system. Okay, so first what you need to do is you need to determine the void ratio if the stress is now increased to 21.6 kp, right? So the void ratio have to find it, and also then we have to calculate the settlement where if the thickness of my soil stratum, the clay stratum is 6 meters, right? So what is the relation for compression index? We just used it. What was the relation? CC is equal to delta E by log of beta 1, right? Now CC I know, it's given as 0.28. Okay, CC I know, so delta E divided by log 10. Sigma 2, what is my sigma 2? 21.6 by sigma 1 is 12. So from here I can get my this value, delta E value. Just calculate 0.28 into log 21.6 divided by 12, but 0.07. 0.07. Just a second. Yeah, so it was asked to ask compute the change in void ratio, right? So this is the change in void ratio. So from the change in void ratio also we can determine the reduction in void ratio. So initially the void ratio was 2.05. So we just deduct 0.07. 0.05. Get 1.97. Okay. So when my load is increased to 21.6 kPa from 12 kPa, my void ratio reduces from 2.05 to 1.97. Okay. So our first part is that. In the second part, what is given? We have to determine the settlement. Okay, you have to determine the settlement if the thickness of the soil is 6 meters. Okay, let us see how to solve. So we know that the consolidation settlement is given by H naught Cc right. We know this. Okay, this how if you ask me how this has come from this simple relation delta H by H equal to delta E by 1 plus E. Okay, this has come from this. Okay, so this delta E we are actually replacing by this Cc into log of uh, this change in stress by initial stress, entry stress by initial stress part, this part. Okay, so this is my consolidation settlement for a normally consolidated soil. Okay, we are using Cc means our soil we have considered that it is normally consolidated, right? Now this initial stress for our initial stress was 12 kPa, and what was the final stress? It was 20. So this is my 21.6 and this is my 12, right? Now this E naught, is actually the initial word ratio before any consolidation has occurred. Okay, so with the given data, how can we find E naught? See, now many people will do mistake here. What they will do is that in place of E naught, they will put 2.05. Okay, but 2.05 is not the initial. At a stress of 12 kPa, the void ratio is 2.05. Okay, this is not my initial void ratio. It means at the parent state, at the natural state, my void ratio was not 2.05. Okay, so we need to find out the initial void ratio. So how can we find out the initial void ratio? So the initial void ratio actually can be related to the compression index using a empirical relation, which is given by this. Cc is equal to 0.54 E naught minus 0.35. So there are many empirical relations that have been given. So we are using this empirical relation. Okay. Cc is equal to 0.54 E naught minus 0.35. Okay. This is an empirical relation which relates my void ratio to the compression index. So now if I put my compression index, what was my compression index? It was 0.28. So if I put 0.28 here, I can determine my E naught as 0.869. Okay. Now this is my initial void ratio. Okay, before the beginning of the test, at the beginning of the test, this was my initial void ratio. Now I have my initial void ratio. Now what can I do is that I can put rest all the values I know, so I can find a settlement. What is my H naught? Nothing but a thickness, which is 6 meter, 6. What is my Cc? 0.28. What is my E naught? 0.869 log 21.6 divided by 12. So please calculate this one. How much settlement? Let us see. Zero point 229 meter equal to 22.9 centimeter. So a lot of 70 centimeter means a lot of settlement. Okay, so around 0.229 meter or 22.9 meter, 22.9 centimeter settlement will be occurring in this one. Okay, I hope this problem was clear. So everything was easy. CC was given, so we found out the change in void ratio. It was very easy. Directly we used the relation of the formula for the CC and found this out. The main catch was this E naught part. Okay, this was the main catchy part here, where we need to use the initial void ratio in order to determine the settlement of this. Okay. Now let us go to the next question. So here the soil profile is actually given to us. Soil profile is given to us, as you can see here. You need to calculate the settlement due to primary consolidation for the 6-meter clay due to the surcharge of 10 kPa. Okay, so there is a surcharge here at the top. Total there is 100 kPa surcharge is there, and if there is a clay layer underline as see, you can see groundwater table is here, so it's completely saturated. The clay layer is completely saturated below a sand layer. Okay, so what we need to determine is we need to determine the our consolidation settlement of the clay layer, right? So determine the consolidation settlement. What we need to do is that our first step means see, obviously here our g and all these values are given, so from there we need to determine. So initially first what you need to determine is the density, the unit weights of the sand, the dry unit weight of the sand, and the submerged unit weight of the clay. These two things we need to determine from the given data. Or actually, the saturated unit weight of the clay is actually directly given to us. Okay, just for the sand, we need to find out the dry unit. Okay, so these things you need to find the unit weight. You need to find out, and the second thing which you need to find out is the initial stress, the geostatic stress of the clay at the clay layer. So what we will do is that we will find out the geostatic, the stress, the effective stress at the center of this clay. Okay, the center of this clay layer. So that will be my, this will actually give my this way. Okay, and this delta sigma value is already known to us. It is 100. It is the increase in the effective stress. So this initial effective stress will be determining at the center of that, and then we also know the our this increasing effective stress delta sigma bar is also given to us. So both these values are given to us. Okay, cc we can find out from the liquid limit. Okay, using an empirical relation we can find out the compression index from the liquid limit value. Okay, the cc we know, height of thickness of the clay layer we know our stress changes. Okay, stress changes, so we know our initial void ratio is given as 0.9, so we can find out our settlement. Now one thing you may ask is, why are we calculating, we are just considering the middle of the clay, we are just, why are we considering the effective stress at the middle of the clay layer? Why not here, why not here? Why are you dividing this layer only two parts and taking the middle? So this is actually a method of averaging. Okay, you are actually averaging the settlement. Here there is some lesser effective stress, here there is more effective stress. So what we are doing, we are just averaging. Okay, by taking the center. Okay, we are just averaging by taking at the center. So one more way which can be by which it can be done is that we can divide it into a number of layers, and after dividing it into a number of layers, at the center of each layer you can find out the settlement. Then you can add it. Okay, we can do this. It is actually a lengthy term. So how, what we need to, so what we can do is just generally see, generally for a simple, for our purposes is fine, we can find out at the middle of the layer. But if you want to go into more detail, what generally it's what it is done is that a normal simple computer, we can write a simple MATLAB code or some any programming simple code we can write. Okay, and we can fix one tolerance value. We can fix one tolerance value that if if we divide the clay layer into two divisions, then this much settlement is coming. If we divide the clay layer into three divisions, then this much accuracy will increase. If we divide into four, then it will be some like there will slight changes in settlement. So we can fix some tolerance value, say 1% or 2%. Then we can write this code. So if the tolerance is reached, then that will be actually the total optimum number of layers that we should divide the layers. Okay. Okay, so just for our purpose, for our for our purpose, it's fine. We just divide, we take at the bottom and directly it's like completely we average. just take at the center of the clay layer and we have origin. No need to divide it in a number of layers. Just let us divide it into two segments by taking it at the center. Let us find out. Okay. So what I told was initially let us first find out the dry unit weight of the sand. So dry unit is nothing but G into gamma w plus 1 plus C. So G is given as 2.66, which is 9.81 by 1 plus 0.72. So please calculate this one. What is the dry unit weight? Okay. Now next we need to calculate the submerged unit weight of the clay. Okay, what is the submerged unit weight of the clay? Sorry, more time. Gamma submerged for clay G minus 1 plus sigma W. So G is given. Okay. Oh, sorry. We don't have to use this one actually. Actually, directly our saturated value is given, right? Our saturated unit weight is actually given to us. So clay nothing but 19.376 minus 9.81, that 9.566. Okay, done. So now let us calculate the effective stress at the center of the layer. Let us calculate. Please tell me. We have already studied this in two classes, so now I think it is clear. So please tell me how to calculate the effective stress here, the center. All the dimensions are given. So here it will be 3 meter. So let us calculate. Please tell me how to calculate the effective stress.
Gamma sand into meter
15.17 into 4 plus
plus 3 into gamma submerged
of the clay. Okay. So we will be getting 89.38. Okay, so this is our effective stress. Now we can calculate the consolidation settlement. Nothing but H into CC by 1 plus E naught log this one. Now what is my CC? CC. So CC, how to find out? So CC is actually given for normally consolidated soil. CC is given 0.009 liquid limit minus 10. Okay, so this is the empirical relation. Okay, so what is my liquid limit? My liquid limit is given to me 60. So 60 minus 10, so it will be nothing but 0.45. So I put the value. What is my H? What is the capital H? What is this? What is capital H? 6 meter. So 6 into 0.45 by 1 plus E naught is given to me. What is E naught? E naught is given 0.9. 0.9 log of 89.38 plus 100 by 89.38. Okay. So let us calculate this. 6 into 0.45, 0.9 into log 89.38 plus 100 by 89.38. 0.463 meters or 46.3 centimeter. So clay layer. So this clay layer will be actually undergoing 46.3 meters or 46.3 centimeters of consolidation settlement. Okay, this is the total settlement that the clay layer will be undergoing at time t is equal to infinity. That is okay, the final settlement, total settlement that will occur. That clay layer. Okay, now let us go to the next problem. So next problem here we have in wait just a second. Yeah, so in a consolidation test, thickness of saturated specimen of clay under consolidation pressure of 100 kPa is 25 mm. Okay, the thickness is given, the water content is given as 15%. On increasing the consolidation pressure to 200 kPa, obviously the thickness of the specimen will reduce, so the thickness is 23.5 mm after the consolidation. The specific gravity is given, we need to find out the compression index of the soil. Okay, we need to find out the compression index. So what we will do is that our water content is given. Okay, so at this level 100 kPa 25 mm, our water content is 15%. So at this point, for 100 kPa, at this point we can find out the void ratio, which will be nothing but E is equal to W into G. S is equal to 1 because the specimen is saturated. It will always be completely saturated. So it is 0.15 into 2.7, right? Then by 0.405. Okay, so this is my initial. Okay, this is my initial at the start of the test. Okay, at the start of the test, you are considering this as the 100 kPa. Okay, this much. Initially, it was the initial state. Now from 100 kPa, you are increasing it to 200 kPa. Correct? So finally, what we are asked to find out the compression. So what is the relation for compression index? So compression index is, so actually this compression index is actually related to my settlement, consolidation settlement. So let me write down the for relation for the consolidation settlement which we have been using. Nothing but 1 plus E naught log sigma. Okay. Okay. Now, what is this settlement here? So around 25, the thickness changes to 23.5. Right. So how much is the settlement that is occurring? 1.5 mm. Okay. So we can put here 1.5 mm. Or CC is unknown. What is the H? H is nothing but 25 mm thickness. We'll put 25. Okay. Now, what is the initial void ratio? Initial void ratio we know 0.405 log. So this is my 200. This is my 100. Okay. So if I solve this, my CC will come as 0.28. Okay. Very simple. E value I know, initial void ratio I know. I have been asked to find the CC. So just use the formula for the consolidation settlement. I determined the CC value. Okay. So the next problem, a clay soil tested in a consolidometer showed a reduction in void ratio from 1.82 to 1.51 when the pressure was increased from 145 kPa to 220 kPa. Okay. Calculate the coefficient of compressibility and the coefficient of volume compressibility. Okay. We need to find out AV and MV. If the soil at the site has a thickness of 4 meter, then determine the consolidation settlement due to the given stress increment. Okay, so let us see how to find this out. So first, you know the coefficient of compressibility. This AV. What is AV? Already calculated before many times. This one, right? So what is my delta E? So let us find out 1.82, 1.52 by 220 minus 1.5 to 4 into 20 to the power minus 3 meter square per kilometer. Acha, put 5-2. Oh, it is 5-1. Okay. Just a second. 5-1. So it will be 4.13. 4.13. Okay, so we got our A. Then it has been as volume compressibility. It's MV. AV by 1 plus E naught. If you do got 1.46 into the power minus 3. So I got my AV, I got my MV. Now it has been asked to us if the soil at the site has a thickness of 4 meters, then determine the consolidation settlement due to the given stress increment. Right. So see, SC by 8 consolidation settlement, as I told you, it's nothing but this. So consolidation settlement is this. Now, what is my AV? AV is delta E by delta stress. Okay, so this delta E I can write it as this delta E I can write it as AV into change in stress by 1 plus E naught into H, isn't it? This delta E I'm replacing as this one. Now this AV by 1 plus E naught is nothing but MV. MV into this into H. So this should give me my settlement. So now MV value I have, I just found it out, 1.46 into 10 to the power minus 3. 46 into 10 to the power minus 3. What is the change in stress? 145 to 220. So 220 minus 145 into H. So what is the H? Which is 4 meters. So if I do this, we'll get the settlement. So 1.46 into 10 to the power minus 3 to 220 minus 145 to 438. 4 meters. Think about 0.438 meter or 43.8 centimeter. Okay. So previously, in the previous problems, we had determined the this consolidation settlement using my CC value, compression index, and in this problem, we determined the our settlement, our consolidation settlement using my AV and MV, that is the coefficient of compressibility and the coefficient of volume compressibility. So using these, we found out a settlement and not using the compression index. Okay. So even if I have my AV value and not a CC value, I can find out my consolidation settlement. Okay, it doesn't matter. We can have CC, we can have AV, we can have MV, anything if we have, we can determine the consolidation settlement. Now let us go to the last problem. Okay. So, so this is for the footing arrangement shown in the figure. Determine the consolidation settlement of the normally consolidated clay layer. Okay, so we take the unit of water as 10 kilonewton per meter cube. So here we can see that one footing is there. Okay, so one footing is there. A load of 400 kilonewton this footing is carrying. The dimension of the footing is given 1.5 meter into 1.5 meter footing. And what we need to do is that we need to determine the consolidation settlement of the clay layer. Okay, so there is sand at the top and the bottom. So the clay will consolidate due to the drainage, and so we need to find out the consolidation settlement. Okay, so how to do this? So first, before similar to the previous problem. Okay, so similar to the previous problem, let us first calculate the value of our this unit weights. Okay, so the unit weight of the sand is actually given to us. Saturated unit weight of my sand is given to us. So this is submerged, groundwater table is here. So total soil is totally submerged. Okay, and the saturated unit weight of sand is given to us. Okay, so what will be the submerged unit weight of sand? 18 minus 10, 8 kilonewton per meter cube, right? Next, we need to find out the submerged unit weight of the clay. So how to find out the submerged unit weight of the clay? Using this. So what is my G? G is given 2.65. Okay. Minus 1 by 1 plus. So E, what is E is as W into G by S. So it is completely saturated. So S is equal to 1. So S equal to WG. So S is 1. So E is equal to W into G. W is given 0.3143 to 0.65 into 10. So let us find out the submerged unit weight of the clay. Got 9 kilonewton per meter. Okay. We got the unit weights. Now, what did you do in the previous problem? We determined the we determined the effective stress at the center of the clay layer. So let us do the same again. So what will be the effective stress at the CC line, at the CC level? The CC level, at this level, what will be the effective stress? Please tell me. What will be the effective stress?
7.5 into
7.5 into
gamma sand
means 8, right? 8 plus how much?
1.5 into
1.5 into 9. Okay. Okay. So we'll get 73.5 kilonewton per meter square at the center. Now we need to determine this. What is the increase in the stress, effective stress due to this footing? Okay. What is the increase in the stress due to this footing? So do you know how to find this out? See, there are many procedures that we are using which we can find out the stress at certain depth. Okay, so but we will be using the simple trapezoidal 2:1 rule to find out the stress. Okay, so do you have any idea how to find this out? How can we find this out? Find the stress. See, at this level, what is the stress that is acting? It is nothing but 4,000 divided by 1.5 into 1.5. That is 1777.78 kPa at this level. Okay, but at this level, it will get distributed, right? The stress will get distributed. So we need to find out the stress at a depth, this depth Z, at a depth Z below. Okay, so what is this depth Z? Depth Z is nothing but, please tell me what is the value of this Z from the figure.
1.5
Yeah,
plus
hmm?
no, bottom 1.5 plus 7.5 minus 1.5, that is 7.5 meters.
7.5 only, 7.5. So means my Z is 1.7.5 meters. So below 7.5 meter from the bottom of the footing, we need to find out the pressure. Okay. So how to find this out? We will be using the simple trapezoidal rule. That is, we will assume that our stress is getting distributed at one vertical is to two horizontal. Okay. Using that, we will find that out. Okay. So relieve my stress. 4,000 kilonewton divided by 1.5 into 1.4, so 1.5 will get changed to see 2 1.5 plus 2 into z, it is 7.5. Okay, I hope you understood this. See, this 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 one is 1.5. Okay, and these two are 2 into 7.5 each. Okay, this is 2 into 7.5. So this is 2 into 7.5. Why 2 into 7.5? Because we are distributing it at one vertical is to two horizontal. Okay, one vertical is to two horizontal. So this one will be 2 into 7.5. This one will be 2 into 7.5. So you can just remember this. Delta sigma z equal to q by q is the total load, b plus twice nz into l plus twice nz, where n is nothing but one vertical is to two, sorry, is two horizontal, so my n is 2 here. Okay, this is 2 is my n, this 2 is my n, and z is my height, which you saw, and b is the width and l is the length. So my length and width both are same here, which are 1.5 1.5 each. So 1.5 plus this one square. So this will give my delta sigma. So let us calculate this. 4,000 divided by plus 14 plus 1.5 square. But second 4.03 meter square. Okay. Now let us find out the consolidation settlement. So before finding the consolidation settlement, our CC is given. Everything is given to us. So H into CC. So what is my H? H is 3 meters. CC is given as 0.38. What is my E naught? Is E naught given to me? No, E naught is not given to me. So I need to find out the E naught. E naught again we can find out by same previous formula which we used. 0.35, 0.38. It can get E naught as 0.5. Okay, so 1.05 log. So what was the initial stress? It was 73.5. Okay, 3 into 0.38 by 2.05 into log. So my C comes out to it as 0.0128 meter. Okay. Okay. So please do this also. Check the result once. Okay. Please check it yourself. Okay. Once check this problem yourself once whether the all the values and everything are same are correct. Okay. So the mean so the problem was actually quite similar to the previous problem that we solved, but The main difference here was that here we had to use this trapezoidal distribution of the load to determine our uh, change in the increase in the stress, increase in the pressure. Rest everything was same. So we using this trapezoidal thing, we determined our change in stresses, change in stress. Then CC also we determined from this, and then we just put this one in our consolidation settlement equation as for the normal consolidated soil, and then we got our settlement. Okay. So I hope all these were clear. And in the next class, we will be solving problems on the this one time rate of consolidation that is based on the Terzaghi's one deconsolidation theory. So we'll be solving those problems. So many means important and conceptual problems which will be dealing with the so where we will be asked to find out the time. Okay, time for 50% settlement. Say how much time will be required for 50% consultation. Okay, so all these things we will be studying in the next class. Okay, so please do this problem by yourself and check the result once. Okay, if it's coming or not. I think it's correct, but still you check from yourself if all these values and all these results are actually correct. Okay. Okay, so thank you. So with this, we will end today's discussion and see you in the next week. Okay, thank you.
Thank you.